Everything in quantum physics changes with time. Particles decay, atoms vibrate, waves collapse. Time is everywhere in the equations. It's the thing that makes quantum mechanics work. But here's what's strange. If you ask a physicist what time is actually made of, the answer isn't what you'd expect. Because unlike matter, which is made of atoms, and unlike light, which is made of photons, time doesn't seem to be made of anything. There's no time particle. There's no smallest confirmed piece of time. Quantum physics can describe how things change with astonishing precision, but it treats time itself as something fundamentally different from everything else it describes. Time is the one thing quantum mechanics uses constantly, but never fully explains. And the deeper you look into why, the more you realize this isn't just a gap in our knowledge. It might be the most important unresolved problem in all of physics. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. Everything around you is made of something. The chair you're sitting on is made of atoms. Those atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of even smaller particles called quarks. Light is made of photons. At every level, when you ask what something is made of, you get an answer. There's always a deeper layer, a smaller building block. This is one of the most powerful ideas in the entire history of science. The idea is that if you want to understand something, you break it apart and look at what's inside. And it works. It works extraordinarily well. We have used this approach to understand matter, to understand light, to understand forces, to understand nearly everything in the physical universe. So it seems perfectly natural to ask the same question about time. What is time made of? But here's where things get strange. Unlike matter, unlike light, unlike forces, time does not seem to be made of anything. Not in the way those other things are. When you break apart a piece of gold, you find gold atoms. When you break apart a gold atom, you find a nucleus and electrons. When you break apart the nucleus, you find protons and neutrons. When you break apart a proton, you find quarks. There's always something inside. But when you try to break apart a second of time, you don't find smaller pieces of time hiding inside it. You don't find time particles. You don't find time atoms. You don't find a fundamental building block of time that snaps together with other building blocks to create minutes and hours and centuries. That's simply not how it works. And the reason this matters so deeply is that quantum physics, the most successful and precise theory in the history of science, the theory that describes how the smallest things in the universe behave, treats time in a way that is fundamentally different from how it treats everything else. There is an asymmetry at the heart of quantum mechanics, a deep and deliberate gap between time and every other physical quantity. And understanding why that gap exists is the first step toward understanding what time might or might not be made of. Let's go back to the beginning. Not the beginning of time itself, but the beginning of how physicists started thinking about time. Because the way physics treats time today did not happen by accident. It evolved over centuries, and at every stage, time played a very specific role in the equations, a role that separated it from everything else. Isaac Newton published his masterwork, the Principia, in 1687. In it, he laid down the laws of motion and the law of universal gravitation. But in order to write those equations, Newton needed a concept of time. And the concept he used was remarkably simple. Time, according to Newton, flows uniformly. It moves forward at a constant rate. It doesn't speed up. It doesn't slow down. It just ticks along in the background. The same everywhere. The same for everyone, regardless of what is happening in the universe. Newton called this absolute time. He wrote that absolute, true, and mathematical time flows equably, without relation to anything external. Think carefully about what that means. Time, in Newton's framework, is not affected by matter. It is not affected by energy. It is not affected by motion or gravity or anything else. It is completely independent of everything. It is the stage on which physics plays out, but it is not part of the play itself. Objects move through space over time. Forces accelerate objects over time. Energy transfers from one system to another over time. But time itself just sits there, ticking, unchanging, unaffected. It is the backdrop against which the drama of the universe unfolds, but it never steps onto the stage as a character. And this worked beautifully for over 200 years. Newton's laws described planetary motion, the trajectories of cannonballs, the mechanics of machines, the orbits of moons. Engineers used them to build bridges and ships and clocks. Astronomers used them to predict eclipses. And throughout all of this, time as the silent backdrop never caused any trouble. Nobody needed to ask what time was made of because it didn't seem to be made of anything at all. It was simply the parameter you plugged into the equations, the clock that ran in the background while physics happened. And this idea, this deeply embedded concept of time as a backdrop rather than a participant, carried forward into quantum mechanics when that theory was developed in the early 20th century. But in quantum mechanics, the consequences of treating time this way became far stranger and far more significant than anyone could have anticipated. Quantum mechanics was built primarily during the 1920s. It was constructed to describe the behavior of atoms, electrons, photons, and other objects at the smallest scales. The classical physics of Newton couldn't explain certain phenomena that experiments were revealing. Atoms emitted light only in specific colors, specific frequencies, rather than in a continuous spectrum. The stability of atoms themselves was a puzzle. According to classical physics, electrons orbiting a nucleus should radiate energy and spiral inward, collapsing the atom in a tiny fraction of a second. Clearly, atoms don't collapse. Something was wrong with the classical picture. And light itself behaved strangely, sometimes acting like a wave spreading out through space, and sometimes like a particle arriving at a specific point. Quantum mechanics solved all of these problems, but it did so by introducing a fundamentally new way of describing physical systems, a way that treated almost everything differently from classical physics. Almost everything, except time. In classical physics, you describe a particle by specifying its exact position and its exact velocity at every moment. From that information, you can predict exactly where it will be at any future moment. The universe is deterministic. If you know the present state with perfect precision, you know the entire future with perfect precision. Quantum mechanics replaced this picture with something profoundly different. Instead of a definite position and velocity, a quantum particle is described by something called a wave function. The wave function does not tell you exactly where the particle is. Instead, it tells you the probability of finding the particle at various locations if you make a measurement. Before you measure, the particle doesn't have a single definite position. It exists in a kind of cloud of possibilities, spread out across space, with some locations being more probable than others. The wave function encodes all the information you can possibly have about the quantum system. It's the complete description. Everything the universe knows about that particle is contained in the wave function, and the way the wave function changes over time is described by the Schrödinger equation. This is the central equation of quantum mechanics. Erwin Schrödinger formulated it in 1926, and it has been confirmed by every single experiment performed in the century since. It is one of the most successful and precisely tested equations in the history of science. Now here is what matters for our question about time. The Schrödinger equation describes how the wave function of a quantum system evolves with time. Time appears in the equation explicitly. It is one of the variables. The equation tells you this. Given the state of the quantum system right now, here is what the state will be an instant from now, and an instant after that, and every moment into the future. But notice something crucial. Time appears in the Schrödinger equation as an external parameter. It is the thing the equation uses to track change. It is the background clock. The wave function changes with time, but time itself is not described by a wave function. Time is not a quantum object in this framework. It is not something that gets measured the way position or energy or momentum get measured. It occupies a fundamentally different role from everything else in the theory. Everything else becomes quantum. Time stays classical. Let me explain this more carefully, because this asymmetry is the key to understanding the entire question, and it's not obvious at first why it's so significant. In quantum mechanics, physical quantities that you can measure are called observables. Position is an observable. You can set up an experiment and measure where a particle is. Momentum is an observable. You can measure how fast a particle is moving. Energy is an observable. You can measure how much energy a system possesses. Spin is an observable. You can measure the intrinsic angular momentum of a particle. Each of these observables is represented mathematically by something called an operator. When you apply the operator to the wave function, you extract the possible measurement outcomes and their probabilities. This is the mathematical machinery of quantum mechanics, and it works with spectacular precision. But time is not an observable in this sense. There is no time operator in standard quantum mechanics. You cannot apply a mathematical operation to a wave function and get the possible results of measuring time the way you can for position or energy. This is not because nobody bothered to try. Physicists have thought about this question extensively for decades. The reason time does not have a standard operator in quantum mechanics is deep and connects to fundamental mathematical constraints that cannot be easily bypassed. In 1933, the physicist Wolfgang Pauli showed that if you tried to construct a time operator that behaved like other quantum observables, you would run into a very serious problem. The energy of the system would have to be unbounded below, meaning it could take on infinitely negative values. There would be no floor, no minimum. Energy could decrease without limit. But real physical systems have a lowest possible energy state, a ground state. Atoms have a ground state. Molecules have a ground state. Every stable physical system we know has a ground state, a minimum energy below which it cannot go. If energy could decrease to negative infinity, nothing would be stable. Everything would cascade endlessly to lower and lower energies. Matter would fall apart. The universe would disintegrate. Since that obviously does not happen, Pauli concluded that a well-behaved time operator, one that works the same way position and momentum operators work, simply cannot exist in standard quantum mechanics. This result is remarkable. It means there is a fundamental asymmetry built directly into quantum mechanics between space and time. Position is a quantum observable. You can measure it. It has an operator. It produces a spectrum of possible outcomes governed by probability. But time is a classical parameter. It ticks along in the background, uniform and unquestioned. The particle exists in space, and you can ask probabilistic questions about where it is. But time is not subject to the same probabilistic treatment. It remains classical, even while everything else around it becomes quantum. You might think this is just a mathematical technicality. Perhaps it's simply the way the equations happen to be written, and it doesn't reveal anything deep about physical reality. But that isn't the case. This asymmetry has real physical consequences, and it points to something genuinely unresolved about the fundamental nature of time. Consider this. In quantum mechanics, when you measure a particle's position, you necessarily disturb its momentum. This is Werner Heisenberg's uncertainty principle, formulated in 1927. The more precisely you determine where a particle is, the less precisely you can know its momentum, and vice versa. This is not a limitation of your measuring instruments. It is not about building better equipment. The particle genuinely does not possess a precise position and a precise momentum simultaneously. Both quantities are quantum observables, and the uncertainty principle describes the fundamental relationship between them. Now, there is a similar-looking relationship between energy and time. The uncertainty in energy, multiplied by the uncertainty in time, must be at least as large as a certain minimum value related to Planck's constant. This looks just like the position-momentum uncertainty relation. It has the same mathematical form, but it is actually quite different in meaning. In the position-momentum case, both quantities are quantum observables with operators. In the energy-time case, energy is a quantum observable, but time is not. The time uncertainty in this relation does not refer to some quantum fuzziness of time itself. It refers to the timescale over which a quantum system's state changes appreciably. It describes how fast things happen, not some fundamental uncertainty in time as a measured quantity. This distinction matters enormously. Quantum uncertainty does affect how things unfold in time. Processes that happen very quickly can involve a wide spread of energies. Processes that involve a very narrow range of energies take a long time to change. This is real, confirmed, practical physics. Short-lived unstable particles have broadly uncertain energies. Long-lived stable states have precisely defined energies. The energy-time relation is physically meaningful and experimentally important, but it does not mean that time itself is a fuzzy, uncertain quantum quantity in the same way that a particle's position is. Time remains the parameter, the backdrop, the thing that tells you when events occur, not a thing that is itself subject to quantum indeterminacy. So here we are. Quantum mechanics, the most precise and successful theory in all of physics, uses time constantly. Every equation references it. Every prediction depends on it. Every experiment measures outcomes at specific times. But the theory treats time as external, as given, as something that exists outside the quantum description of the world. The theory describes how quantum states evolve with time, but it says nothing about what time itself is made of. It doesn't even treat time as the kind of thing that could be made of something. This is what makes the original question so deliberately strange. Asking what time is made of is not like asking what water is made of. When you ask what water is made of, there is a clear and definitive answer. Water is made of molecules, each containing 2 hydrogen atoms and 1 oxygen atom. The question has a concrete answer because water is a substance, and substances are made of parts. But time is not a substance in that same sense. In quantum mechanics, time is more like the framework that allows you to ask questions about substances in the first place. It is the coordinate that organizes events. It is the measure of change, but it is not itself one of the things that changes. Imagine a movie. The movie contains characters, scenery, dialogue, plot. All of those things are part of the content of the movie. You can analyze them, break them apart, study their composition. But the movie also has a timeline. Frame 1 comes before frame 2, which comes before frame 3. The timeline is what allows the movie to unfold. Without it, you just have a jumbled pile of disconnected images with no order, no narrative, no change. Now you can ask what the characters are made of. They're made of pixels. You can ask what the scenery is made of, also pixels. But asking what the timeline is made of is a fundamentally different kind of question. The timeline isn't made of pixels. It's the structure that organizes the pixels into a meaningful sequence. It's the framework, not the content. In quantum mechanics, time plays an analogous role. It is the framework that organizes quantum events into sequences. It tells you what comes before and what comes after. It allows the wave function to evolve, particles to interact, measurements to produce outcomes at specific moments. But it is not itself one of the quantum events. It is not made of the same stuff that particles and fields are made of. It sits apart. And that separation is built directly into the mathematical structure of the theory. This is not because physicists arbitrarily decided it should be this way. It is because every serious attempt to treat time like just another quantum observable has run into deep and persistent mathematical difficulties. Pauli's argument from 1933 is one example, but there are others. The entire mathematical framework of quantum mechanics, from its axioms to its most sophisticated applications, was built around the idea that time is external. And that framework works. It predicts the behavior of atoms, molecules, solids, liquids, gases, semiconductors, superconductors, lasers, transistors, nuclear reactions, and every other quantum phenomenon we have ever tested with astonishing accuracy. The asymmetry between space and time in quantum mechanics is not a flaw to be corrected. It is a foundational feature that has been validated by a century of increasingly precise experiments. But it is a feature that raises profound questions, because even though it works, it leaves time fundamentally unexplained. Standard quantum mechanics tells you everything about how things change with time, but reveals nothing about what time itself actually is. It gives you the rules for how the game unfolds, but doesn't tell you what the game clock is made of, or why it ticks. And for a long time, physicists could live with this. They could use quantum mechanics to make incredibly precise predictions about atoms and particles and light, without ever needing to address the deeper nature of time. The theory worked, and that was enough. But there is a problem looming on the horizon, a problem that makes this gap in our understanding impossible to ignore. Because quantum mechanics is not the only fundamental theory we have about the physical world. There is another theory, equally well tested, equally successful in its own domain, that tells us something very different about time. And when you try to combine these two theories into a single unified framework, the fact that quantum mechanics treats time as an external parameter becomes a serious, perhaps the most serious, obstacle. That other theory is general relativity. Albert Einstein's theory of gravity, published in 1915. And in general relativity, time is not external at all. Time is not a fixed backdrop that ticks uniformly in the background, regardless of what happens. Time is part of the physical structure of the universe itself. It bends, it stretches, it slows down near massive objects, it speeds up far from gravity. It is woven together with the three dimensions of space into a single four-dimensional fabric called spacetime. And that fabric is dynamic. It curves in response to matter and energy. It ripples when massive objects accelerate. It warps dramatically around black holes. Time, in general relativity, is physical. It is part of the content of the universe, not just the framework. This creates a direct tension with quantum mechanics. Quantum mechanics says time is an external parameter, a fixed and uniform background that doesn't change and isn't subject to quantum rules. General relativity says time is part of the physical fabric of the universe, dynamic and responsive and deeply entangled with gravity and matter. Both theories are spectacularly successful in their own domains. Quantum mechanics describes atoms and particles with extraordinary precision. General relativity describes gravity, black holes, gravitational waves, and the large-scale expansion of the universe with equal precision. But they describe time in fundamentally incompatible ways. And this incompatibility is not an abstract academic curiosity. It is the central obstacle preventing physicists from constructing a complete theory of quantum gravity, a theory that would unify quantum mechanics and general relativity into a single coherent framework. Such a theory would need to handle time in a way that is consistent with both the quantum treatment and the gravitational treatment. It would need to explain how time can appear as a fixed external parameter in one regime and as a dynamic, bending, stretching physical entity in another. Or it would need to demonstrate that one of these descriptions is more fundamental and the other is an approximation that breaks down under certain extreme conditions. This is why the question of what time is made of is not merely a philosophical curiosity. It is a concrete and urgent physics problem. If time is truly external, as standard quantum mechanics suggests, then general relativity's description of dynamic curved spacetime must somehow emerge from something deeper, something more fundamental that doesn't include time as a physical ingredient. If time is truly physical, as general relativity suggests, then quantum mechanics' treatment of time as a fixed background must be an approximation, one that works beautifully under normal conditions, but fails catastrophically under extreme ones, near black holes, at the birth of the universe, at the very smallest scales of existence. Either way, something has to give. And whatever gives will tell us something profound about the ultimate nature of time. Whether it has a deeper structure we have not yet seen, whether it is fundamental or emergent, whether it is truly made of something we haven't yet discovered, or whether asking what time is made of is simply the wrong question applied to the wrong concept. For now, let's stay with what we know for certain. In standard quantum mechanics, time is an external parameter. It is not a quantum observable. It does not have a wave function. It is not subject to quantum uncertainty in the way that position and momentum are. Every quantum system in the universe evolves with time, but time itself is not one of those quantum systems. Electrons are quantum objects. Photons are quantum objects. Atoms, molecules, and fields are quantum objects. Time is not. And so when you ask what time is made of according to quantum physics, the honest answer, the one that no physicist would disagree with, is that quantum physics does not address this question. It uses time. It depends entirely on time. It cannot function for a single calculation without time. But it does not describe time as being made of anything. Time, in quantum mechanics, is simply there, given, assumed, the silent clock that runs in the background while everything else in the universe obeys quantum rules. That silence, that refusal of the theory to say anything at all about the nature of time itself, is one of the most important and revealing silences in all of physics. It tells us that our most fundamental theory of the microscopic world is not wrong, but incomplete. It describes with breathtaking accuracy how everything changes with time, but it leaves the deepest question about time itself entirely unanswered. What is this thing that all of quantum physics depends on but never explains? Is it truly fundamental, existing independently of everything else in the universe? Or is it something that emerges from a deeper layer of reality we have not yet uncovered? And if our clocks, our best clocks, the most precise instruments humanity has ever built, are themselves made of quantum systems, what exactly is the relationship between the quantum world and the time it keeps? Those questions demand answers, and the answers, as we're about to discover, are far stranger and more surprising than the questions themselves. So if quantum mechanics treats time as an external parameter, something outside the theory rather than inside it, you might wonder how we actually measure time in practice. Because here is something fascinating. The most precise clocks ever built by human beings are quantum mechanical devices. They exploit quantum properties of atoms to keep time with an accuracy that borders on the incomprehensible. Physical clocks, real clocks, the instruments that actually define what a second is, are made of quantum systems, atoms, energy levels, photons, the very machinery of quantum mechanics. And this fact creates a distinction that is easy to miss, but absolutely critical to understanding our question. The distinction between measuring time and explaining what time fundamentally is. Because these are not the same thing, and confusing them leads to some of the deepest misunderstandings about what quantum physics actually tells us about the nature of time. To understand why this distinction matters, let's first think about what a clock actually does. At its core, every clock in history has done the same basic thing. It counts a repeating event. Something happens over and over again at a regular rate, and the clock counts how many times it happens. That is all a clock is, a counter of repetitions. A sundial counts the repeating motion of a shadow as Earth rotates. A pendulum clock counts swings. A wristwatch counts oscillations of a tiny quartz crystal vibrating inside its case. In each case, the clock does not create time. It simply counts something that repeats, and we use those counts to measure how much time has passed. The clock is a measuring instrument, like a ruler measures distance. The ruler does not create distance, and the clock does not create time. But the quality of a clock depends entirely on the regularity of the repeating event it counts. If the event is perfectly regular, repeating at exactly the same interval every single time, the clock is perfect. If the event is slightly irregular, sometimes faster, sometimes slower, the clock drifts. It becomes inaccurate. It tells you the wrong time. So the entire history of timekeeping has been a search for the most perfectly regular repeating event in nature. Something that ticks at exactly the same rate every single time, without variation, without error, forever. And that search led directly to quantum mechanics. For most of human history, the best available repeating events were astronomical. The rotation of the Earth, the orbit of the Earth around the Sun, the phases of the Moon. These are regular enough for everyday life, but they are far from perfect. Earth's rotation is actually slowing down over time due to tidal interactions with the Moon. Days were shorter hundreds of millions of years ago. The length of a day is not truly constant. It changes over centuries, and even from year to year, due to earthquakes, shifts in ocean currents, and changes in the distribution of mass inside the planet. If you define a second based on Earth's rotation, your second is slowly changing without you knowing it. In 1656, Christian Huygens built the first practical pendulum clock. A pendulum swings back and forth at a rate determined by its length and the local strength of gravity. Pendulum clocks could keep time to within about 15 seconds per day, and later designs improved that to a fraction of a second per day. But pendulums are affected by temperature, air pressure, and vibrations. They are mechanical devices, and mechanical devices are inherently imperfect. Their accuracy has a ceiling that no amount of engineering can break through. In the 1920s and 1930s, quartz crystal oscillators transformed timekeeping. When you apply an electric current to a quartz crystal cut to the right shape and size, it vibrates at a very precise frequency, determined by its physical dimensions. A typical quartz crystal in a wristwatch vibrates 32,768 times per second. This is far more regular than any pendulum could ever be. Quartz clocks can keep time to within a few seconds per month. That is good enough for daily life, good enough for most technology, good enough for nearly everything most people need. But it is nowhere near good enough for the most demanding applications in physics, navigation, or telecommunications. The problem with quartz crystals is that they are manufactured objects. No two crystals are exactly identical. Temperature affects their vibration frequency. They age over time, their properties slowly drifting. They are regular, impressively regular, but they are not perfectly regular. And to push timekeeping to the next level of precision, physicists needed something that nature itself guaranteed would be identical everywhere in the universe. Not something built by human hands, but something built by the laws of physics themselves. They found it in atoms. And this is where quantum mechanics enters the story of timekeeping in the most powerful way imaginable. One of the fundamental discoveries of quantum mechanics is that atoms can only exist in specific, discrete energy states. An electron inside an atom does not have a continuous range of possible energies. It occupies specific energy levels, like steps on a staircase, separated by definite gaps. It can stand on one step or another, but never between steps. And when it transitions between two levels, it absorbs or emits a photon whose frequency corresponds exactly to the energy difference between those levels. This is not approximate. It is not a rough match. It is exact, to a degree of precision that is almost impossible to overstate. Every cesium atom in the universe, every single one that exists or has ever existed or will ever exist, has exactly the same energy levels. Not similar energy levels, not closely matched energy levels, exactly the same. A cesium atom in a laboratory in London has precisely the same energy levels as a cesium atom in Tokyo, a cesium atom drifting through interstellar space, a cesium atom in a galaxy billions of light years away. This is guaranteed by quantum mechanics. The energy levels of an atom are determined entirely by the fundamental constants of nature, the masses of the subatomic particles, the strength of the electromagnetic force, the value of Planck's constant. These constants are the same everywhere in the universe, so the energy levels, and therefore the frequencies of light emitted and absorbed during transitions, are the same everywhere. This is profoundly different from anything in the classical world. Two pendulums might be very similar, crafted by the same maker from the same materials, but they are never truly identical. Two quartz crystals might vibrate at nearly the same frequency, but there is always some tiny difference between them. But two cesium atoms are absolutely, fundamentally, quantum mechanically identical. Not because they were manufactured carefully, not because someone inspected them for quality control, but because the laws of quantum mechanics demand it. Identity is not a manufacturing achievement here. It is a law of nature. In 1945, a physicist named Isidore Rabi proposed using the natural transitions of atoms as the basis for a new kind of clock. The idea was simple and brilliant. If atoms have transitions at precise frequencies, and those frequencies are the same for every atom of a given type everywhere in the universe, then you have a natural frequency standard, a repeating event that nature guarantees is perfectly regular. No manufacturing tolerances, no aging effects, no temperature sensitivity in the transition frequency itself. Just the same exact frequency, every single time, everywhere, forever. The first truly accurate cesium atomic clock was built by Louis Essen and Jack Parry at the National Physical Laboratory in England in 1955. Here is how it works in principle. Cesium-133 atoms have two very closely spaced energy levels in their ground state. These two levels differ by a tiny amount of energy, and the transition between them corresponds to a specific microwave frequency. When you expose cesium atoms to microwave radiation at exactly the right frequency, the atoms absorb the radiation and jump from the lower energy level to the higher one. If the microwave frequency is even slightly wrong, too high or too low by the tiniest fraction, the absorption drops off dramatically. The atoms simply do not respond. They are exquisitely sensitive to whether the frequency is right. The clock works by carefully tuning the microwave frequency until the maximum number of atoms make the transition. At that precise point, you know the microwave frequency exactly matches the atomic transition frequency. The atoms are confirming that the frequency is correct, and then you count the oscillations of that microwave field. Each oscillation is one tick of the clock. The frequency of this particular transition in cesium-133 is exactly 9,192,631,770 oscillations per second. That number is not arbitrary. It is not a convention chosen for convenience. It is a physical property of the cesium-133 atom, determined by the fundamental constants of nature and the internal quantum structure of the atom. When the clock counts that many oscillations, exactly 1 second has passed. Think about what this means. The clock is counting microwave oscillations. It counts nearly 9.2 billion of them and calls that interval 1 second. The extraordinary precision comes from the sharpness of the atomic transition. If the microwave frequency drifts even slightly from the correct value, the number of atoms making the transition drops noticeably, and the clock's feedback system corrects it. The atoms themselves act as a reference, a natural and incorruptible frequency standard, against which the microwave source is continuously checked and adjusted. It is a feedback loop. The atoms keep the microwave source locked to the correct frequency. The clock counts the oscillations of that locked source, and the result is timekeeping of almost unbelievable accuracy. In 1967, the International Committee for Weights and Measures officially redefined the second based on this cesium transition. Before that, the second had been defined astronomically, based on the rotation or orbit of the Earth. But Earth's rotation is irregular, and tying the fundamental unit of time to an irregular process was a problem for precision science. So the second was redefined. 1 second is now, by definition, the time it takes for a cesium-133 atom to complete exactly 9,192,631,770 oscillations of its ground state hyperfine transition. Time, at the level of official international standards, is measured by counting quantum events. The best modern cesium fountain clocks are accurate to about 1 part in 10 quadrillion. That means they would gain or lose approximately 1 second over a span of about 300 million years. This is astonishing precision, far beyond what any mechanical or electronic device could achieve, and it is made possible entirely by quantum mechanics. Without discrete energy levels, without the quantum mechanical guarantee that all cesium atoms are identical, without the sharp and precise frequencies of atomic transitions, this kind of accuracy would be physically impossible. Quantum mechanics does not just help with timekeeping, it is what makes modern timekeeping work. But cesium clocks are no longer the most precise timekeeping devices we have. They have been surpassed by something even more extraordinary. Optical lattice clocks represent the current frontier of timekeeping, and they push precision into territory that seems almost absurd. Instead of using microwave transitions, which oscillate roughly 9 billion times per second, optical lattice clocks use transitions at optical frequencies, the frequencies of visible or near-visible light. These frequencies are vastly higher. An optical transition might oscillate at several 100 trillion times per second, tens of thousands of times faster than microwaves. More oscillations per second means finer time resolution, just as a ruler with millimeter marks gives you more precision than one with only centimeter marks. The atoms used in optical lattice clocks are typically strontium-87 or ytterbium. These atoms are cooled to temperatures just a tiny fraction of a degree above absolute zero using laser cooling techniques. At these temperatures, the atoms move incredibly slowly, nearly motionless. This reduces Doppler effects that would otherwise blur the transition frequency and compromise the clock's accuracy. The cooled atoms are then trapped in a lattice, a regular grid structure created by intersecting laser beams. The lasers create a pattern of standing waves, peaks and valleys of light intensity. The atoms settle into the valleys of this pattern, held in place like eggs sitting in the compartments of a carton. Once trapped, the atoms are probed with a separate laser tuned to their specific optical transition frequency. The same principle applies as in cesium clocks. When the laser frequency exactly matches the atomic transition, the atoms absorb the light and jump to a higher energy state. When the frequency is off, they do not respond. The clock counts the oscillations of this precisely tuned laser field. Because the oscillation frequency is so much higher than microwaves, the clock can slice time into far finer intervals. The best optical lattice clocks today achieve accuracies that are almost beyond comprehension. They would lose or gain approximately 1 second over 15 billion years. That span is longer than the current age of the universe. If one of these clocks had been started at the moment of the Big Bang and had been running continuously ever since, it would still not have gained or lost a full second by today. These are the most precise measuring instruments humanity has ever constructed, for any physical quantity in any field of science. And they are so precise that they can directly detect the warping of time by gravity. Because of general relativity, clocks at slightly different heights in a gravitational field tick at slightly different rates. A clock sitting on a table runs very slightly faster than an identical clock sitting on the floor, because the table clock is farther from the center of the Earth, and therefore in a slightly weaker gravitational field. The effect is real. It is predicted precisely by Einstein's general relativity, and optical lattice clocks are sensitive enough to measure this difference over height separations of just a few centimeters. They are directly sensing how gravity bends the flow of time. This extraordinary precision is not just a laboratory achievement, it has practical consequences that affect your life every day. The Global Positioning System, GPS, depends on atomic clocks aboard its satellites. Each GPS satellite carries cesium or rubidium atomic clocks. Your GPS receiver works by measuring the tiny differences in the arrival times of signals from multiple satellites simultaneously. Those time differences reveal how far you are from each satellite, and from those distances, your precise position on the surface of the Earth is calculated. The precision required is remarkable. A timing error of just 1 microsecond, 1 millionth of a second, translates into a position error of about 300 meters. To give you accurate navigation down to a few meters, the satellite clocks must be synchronized to within a few billionths of a second. Only atomic clocks can achieve this level of synchronization. Without quantum mechanics, GPS would not work. And there is another complication. The satellites are moving at high speed relative to you and are positioned far above Earth's surface. Special relativity predicts that moving clocks tick slightly slower. General relativity predicts that clocks farther from a massive object tick slightly faster. Both effects are small, but they are real, and they accumulate rapidly. Without correcting for both relativistic effects every single day, GPS positions would drift by several kilometers within just 24 hours. The fact that GPS works accurately, that it guides you reliably to a destination, or helps an airplane land safely in fog, is direct everyday confirmation that both quantum mechanics and relativity correctly describe how time behaves. There is another way quantum mechanics reveals the relationship between quantum systems and time that goes beyond clocks, and it comes from one of the most famous phenomena in all of physics: radioactive decay. Certain atomic nuclei are unstable. They will eventually break apart, releasing energy and transforming into a different element. This process is governed entirely by quantum mechanics, and it has a very specific and deeply strange property. You cannot predict when a particular unstable atom will decay, not because you lack information, not because your instruments are insufficiently precise, but because the universe itself does not determine the outcome until it happens. The decay is genuinely random at the level of the individual atom, But here is what makes this remarkable for our question about time. Even though the individual decay is unpredictable, the statistical behavior of large numbers of identical atoms is extraordinarily precise. If you have 1 trillion atoms of a radioactive substance, you can predict with great accuracy what fraction will have decayed after a specific interval. This is the concept of a half-life. After one half-life, approximately half the atoms will have decayed. After 2 half-lives, approximately 1/4 of the original atoms remain. After 3 half-lives, 1/8. The pattern is perfectly regular, perfectly predictable, governed by a precise mathematical law. The half-life of carbon-14, for example, is approximately 5,730 years. This number is determined by quantum mechanics, by the specific quantum properties of the carbon-14 nucleus, and it is the same everywhere in the universe. Physicists use it to date archaeological artifacts, geological samples, and ancient biological remains with remarkable accuracy. So quantum mechanics gives you perfect statistical regularity, unfolding over time while maintaining complete unpredictability for any individual event. The process happens in time. The half-life is measured in units of time. The statistical law describes how the population of atoms changes with time, but time itself is not what is being randomized. The quantum uncertainty is in the nuclear state, in whether a particular atom has decayed or not. Time remains the orderly background against which this quantum randomness plays out. There is an even stranger phenomenon that sharpens this point further. It is called the quantum Zeno effect. In the 1970s, physicists realized that if you repeatedly observe an unstable quantum system at very short intervals, checking again and again whether it has decayed, the rate of decay actually slows down. The more frequently you observe the system, the slower it evolves. In the extreme limit, if you could observe it continuously, the system would never decay at all. It would be frozen in its initial state by the act of observation itself. This sounds paradoxical, but it has been confirmed experimentally. It is a direct consequence of the mathematics of quantum mechanics, specifically of how the wave function evolves between measurements and how measurement resets the quantum state. Each observation projects the system back into its initial, undecayed state. If the interval between observations is short enough, the system never accumulates enough quantum amplitude in the decayed state to have a significant probability of being found there. The quantum Zeno effect reveals something deep about the relationship between quantum evolution and time. The rate at which a quantum system changes depends on how it is observed. Observation and the passage of time interact in a way that has no analogue in classical physics. But notice carefully what is happening. The quantum state is what changes or does not change. The quantum state is what is affected by observation. Time itself is not being frozen by the Zeno effect. Time continues to pass at its normal rate. The clock in the laboratory keeps ticking regardless of how often the experimenters check the unstable atom. What changes is how the quantum system evolves within that steadily flowing time. The quantum Zeno effect is about quantum states and measurement, not about time itself. Time provides the framework. Quantum mechanics provides the drama happening within that framework, and the two remain fundamentally distinct. So here we are. We have clocks of breathtaking precision, clocks that count quantum transitions with almost perfect regularity, clocks that define the official international standard of the second, clocks that detect the warping of time by gravity across height differences smaller than the length of your hand, clocks built entirely from quantum systems, operating according to quantum mechanical principles. And all of this might seem to suggest that we understand what time is made of, that since our clocks are quantum, time must be quantum too, that since we can measure time with such extraordinary precision, we must have grasped its fundamental nature. But this is exactly where the critical distinction comes in, and it is a distinction that cannot be emphasized enough. Measuring time is not the same as understanding what time is. A clock tells you how much time has passed. It tells you this with spectacular accuracy, but it does not tell you what time itself is made of. It does not tell you why time flows in one direction. It does not tell you whether time is fundamental or emergent. It does not tell you whether time has a deeper structure at scales too small for any clock to reach. It tells you nothing whatsoever about the ultimate nature of the thing it measures. Think about it this way. A thermometer measures temperature with great precision, but the thermometer does not tell you what temperature fundamentally is. It took physicists over a century to understand that temperature is actually the average kinetic energy of molecules in motion. The thermometer measures the effect. The deeper explanation, that temperature arises from the collective behavior of enormous numbers of tiny particles, required a completely separate theory called statistical mechanics. The thermometer was essential for gathering data, but the explanation of what temperature actually is came from insights that went far beyond what any thermometer could reveal. Similarly, a clock measures time. It counts oscillations. It compares one interval to another. But the deeper question, what time actually is at the most fundamental level, whether it is a basic feature of reality or something that emerges from more basic quantum processes, whether it has structure at the smallest conceivable scales or is perfectly smooth and continuous. Those questions are not answered by building a more precise clock. No matter how many decimal places of precision you add, the clock still only tells you how much time has passed. It does not tell you what passed. The cesium atom does not contain time inside it. The quantum transition from one energy level to another does not produce time. Time is what the transition happens within. The atom vibrates in time. The photon is emitted at a specific moment in time. The clock counts events that occur in time, but none of this tells us what time itself is. The clock is embedded in time the way a fish is embedded in water. The fish uses the water. The fish depends on the water. The fish can tell you a great deal about how water behaves, how it flows, how it moves, what it feels like to swim through. But the fish does not explain what water is made of. That requires a completely different kind of investigation. And this leads to another important point that is widely misunderstood. Quantum mechanics involves probability and uncertainty. Measurements of quantum systems produce inherently random results. You cannot predict exactly when a particular radioactive atom will decay. You cannot predict exactly where a particular electron will be found when you look for it. These outcomes are genuinely random, not because of incomplete knowledge, not because of imperfect instruments, but because nature itself is fundamentally probabilistic at the quantum level. This is what quantum mechanics tells us, confirmed by a century of experiments. This leads some people to conclude that time itself must also be uncertain or random at the quantum level. That quantum uncertainty somehow makes time fuzzy, unreliable, or even illusory. But this is a significant misunderstanding of what quantum uncertainty actually means and what it applies to. Quantum uncertainty applies to quantum observables. Position is a quantum observable. Momentum is a quantum observable. Energy and spin are quantum observables. These are the things that have inherent quantum randomness. When you measure them, you get one of several possible outcomes, each with a certain probability. The specific outcome is genuinely unpredictable until the measurement occurs. But as we explored earlier, time is not a quantum observable in standard quantum mechanics. There is no time operator. Time is the parameter against which quantum events unfold. The randomness is in the outcomes of measurements, not in the time at which those measurements take place. When a radioactive atom decays, the moment of decay is uncertain. But that uncertainty is really about the quantum state of the atom, not about the nature of time. The atom exists in a quantum superposition of decayed and not yet decayed. The uncertainty concerns which state you will find the atom in when you check. Time itself keeps flowing smoothly and deterministically throughout the process. Here is another way to see this. The Schrödinger equation, which governs how quantum states evolve, is itself perfectly deterministic. Given the state of a quantum system at one moment, the equation tells you with perfect mathematical certainty what the state will be at any future moment. The wave function evolves smoothly, predictably, without any randomness at all. Randomness enters only at the moment of measurement, when the wave function appears to collapse to a specific outcome. But the evolution between measurements is perfectly orderly and governed entirely by the deterministic flow of time. Time in quantum mechanics is not random. It is not fuzzy. It is not uncertain the way position and momentum are uncertain. It is the reliable, orderly, deterministic background against which all quantum events unfold. This connects to an even broader misconception. The idea that because quantum mechanics is strange and counterintuitive, time must be somehow unreal, that time is just an illusion, that it does not genuinely exist. You encounter this claim surprisingly often in popular science writing, in documentaries, sometimes even in statements by well-known physicists, quoted without sufficient context. But it is deeply misleading. Time may be mysterious. Its fundamental nature may remain unresolved. We may not yet know what it is made of, or whether it is fundamental or emergent. But that does not mean time is unreal. The evidence that time exists and plays a central role in physics is overwhelming and unambiguous. Every experiment ever performed in quantum mechanics confirms that quantum states evolve in time. Every atomic clock ever built confirms that time can be measured with precision beyond anything else in science. Every observation in physics, from the decay of subatomic particles to the expansion of the universe, depends on time being real and functional. When physicists say time is mysterious, they mean its deeper nature has not been fully explained. They do not mean it does not exist. There is a vast difference between those two statements. Gravity was mysterious long before Newton described it mathematically, and even more mysterious before Einstein revealed it as the curvature of spacetime. But gravity was real the entire time, pulling objects toward each other, holding the moon in its orbit, shaping the evolution of the cosmos, regardless of whether anyone understood it. Time is in a similar position today. It works. It is real. We can measure it with unparalleled precision. We can use it to make predictions of extraordinary accuracy. But we do not yet fully understand what it is at the deepest level. And that gap between measurement and understanding is one of the most important gaps in all of science. So what have we actually learned from quantum clocks? We have learned that quantum mechanics provides the most regular oscillators in nature. Atomic transitions have frequencies determined by fundamental constants and identical for every atom of a given type, everywhere in the universe, for all time. We have learned that these oscillators can measure time with precision exceeding 1 part in 10 to the 18th power. We have learned that quantum mechanics is not just helpful for timekeeping, it is absolutely essential. Without quantum physics, the precision of modern atomic clocks would be completely impossible. But we have also learned something more subtle and perhaps more important. We have learned that measuring time, even measuring it with nearly perfect precision, does not tell you what time is. The clock measures intervals. It tells you that a specific interval lasted exactly this many atomic oscillations, but it does not reveal what an interval of time actually is at the deepest level. It does not tell you whether time is smooth or grainy. It does not tell you whether time is a fundamental ingredient of reality or something that emerges from more basic processes. It does not tell you whether time could be made of something we simply have not discovered yet. And the situation becomes even stranger when you bring gravity into the picture. Because we do not just have one fundamental theory about time, we have two, and they disagree with each other in ways that go straight to the heart of the question we are trying to answer. Quantum mechanics treats time as an external parameter, a flat, uniform, classical backdrop that does not bend, does not stretch, does not change depending on where you are or how fast you are moving. In quantum mechanics, time is essentially still Newton's absolute time, dressed in the language of wave functions and probability amplitudes, but playing the same role it always has, a fixed stage on which the quantum drama plays out. But general relativity tells us something completely different. In Einstein's theory of gravity, time is not fixed, it is not uniform, it is not external. Time is part of the physical fabric of the universe itself. It bends near massive objects. It slows down in strong gravitational fields. It is woven together with the 3 dimensions of space into a single 4-dimensional structure called spacetime. And that structure is dynamic. It curves in response to matter and energy. It ripples when massive objects collide. Time, according to general relativity, is physical. It is part of the content of the universe, not merely the backdrop. We just saw this directly with optical lattice clocks. They are so extraordinarily precise that they can measure the difference in the rate of time between 2 points separated by only a few centimeters in height. Time genuinely runs at different rates at different locations in a gravitational field. This is not an illusion. It is not a malfunction of the clocks. It is a real, confirmed, experimentally verified physical effect, predicted by general relativity over a century ago. And it means that time simply cannot be the simple, uniform, unchanging backdrop that standard quantum mechanics assumes it is. Something deeper is going on, and the tension between these two descriptions of time, the quantum mechanical version and the gravitational version, leads to one of the most profound unsolved problems in all of physics. We have now reached the heart of the tension. On one side stands quantum mechanics, spectacularly successful at describing atoms, particles, and forces, but treating time as an external parameter that ticks uniformly in the background, unaffected by anything happening in the universe. On the other side stands general relativity, equally successful at describing gravity, space-time, and the large-scale structure of the cosmos, but treating time as something physical, dynamic, woven into the fabric of reality itself, curving and stretching in response to matter and energy. Both theories are confirmed by mountains of experimental evidence. Both are essential for understanding the universe, and they describe time in ways that are fundamentally incompatible. This incompatibility is not a minor technical disagreement. It is a deep, structural, conceptual clash about what time actually is. You cannot build a complete theory of the universe without reconciling these two descriptions. Something has to give, and whatever gives will transform our understanding of time at the most fundamental level. To see why this clash is so deep, let's look more carefully at what general relativity actually says about time, because it goes far beyond just saying that clocks run at different rates near massive objects. It says something much more radical. It says that time and space are not separate things. They are a single, unified entity called spacetime. And spacetime is not just a passive arena in which things happen. It is itself a physical thing, a dynamic structure that interacts with matter and energy and changes in response to them. This idea traces back to 1908, when Hermann Minkowski, who had been one of Einstein's mathematics professors, realized that special relativity could be understood geometrically. Einstein had shown in 1905 that measurements of time and space depend on how fast the observer is moving. Moving clocks tick slower. Moving objects shrink in the direction of motion. These effects are not illusions. They are real, physical consequences of the fact that the speed of light is the same for all observers. Minkowski saw that these effects made perfect sense if you thought of time and space not as separate dimensions, but as a single four-dimensional structure. 3 dimensions of space, 1 dimension of time, woven together into a unified whole. Events in the universe don't just have locations in space, they have locations in space-time. And the geometry of that space-time determines the relationships between events, which ones can influence which, how much time elapses between them, and how distances and durations are measured by different observers. Einstein took this idea and extended it dramatically with general relativity in 1915. In special relativity, space-time is flat. It has a fixed, uniform geometry that does not change. But Einstein showed that when gravity is present, space-time curves. Matter and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. Gravity is not a force pulling objects together across empty space. It is the curvature of space-time itself, guiding objects along curved paths through a 4-dimensional landscape. The Earth does not pull an apple toward it by reaching out with an invisible hand. Instead, the Earth's mass curves the space-time around it, and the apple follows the curved path through that space-time. It is falling freely through curved geometry. And here is what matters most for our question. Time is part of that geometry. When space-time curves near a massive object, the time part curves along with the space part. This is not a metaphor. It is not an analogy. It is a precise mathematical statement about the structure of the equations. Time near a massive object literally passes at a different rate than time far from that object. We confirmed this directly with the optical lattice clocks discussed earlier, detecting differences in the rate of time over height separations of just centimeters. Gravitational time dilation is one of the most precisely confirmed predictions in all of physics. It is real, measurable, and inescapable. In extreme environments, the curvature of time becomes dramatic. Near a black hole, space-time is so severely curved that time slows down enormously compared to distant regions. At the event horizon, the boundary of the black hole, the curvature becomes so intense that from the perspective of a distant observer, time at the horizon appears to stop completely. Objects falling toward the black hole appear to freeze at the horizon, their light redshifting endlessly, growing dimmer and dimmer, taking forever to cross that boundary from the outside perspective. From the perspective of the falling object itself, time continues normally. It crosses the horizon in finite time by its own clock. But the outside universe ages enormously during what the falling object experiences as a brief descent. Time depends entirely on where you are and how space-time is curved around you. The universe's expansion is another example. General relativity describes the universe as an expanding space-time. Space itself is stretching, carrying galaxies apart. But it is not just space that is involved. The expansion affects time as well. Light from distant galaxies is stretched as it travels through expanding space, arriving at our telescopes with longer wavelengths and lower frequencies. This cosmological redshift is a direct consequence of the space-time structure of the universe. So in general relativity, time is physical. It bends, it stretches, it depends on the distribution of matter and energy. It is part of the dynamic fabric of the universe. It is emphatically not a fixed, uniform external backdrop. It is as physical as space itself, as physical as gravity itself, because it is part of gravity. Gravity is the curvature of space-time, and time is one of the dimensions of space-time that curves. Now bring quantum mechanics back into the picture. In quantum mechanics, time is a fixed external parameter. It appears in the Schrödinger equation as the independent variable against which everything else evolves. It does not curve. It does not bend. It does not depend on what is happening in the system being described. It just ticks along uniformly in the background. When physicists tried to combine these two theories, tried to build a quantum theory of gravity that would describe space-time itself as a quantum system, they ran into a problem so deep and so strange that it has been debated for over 60 years. It is called the problem of time in quantum gravity, and it reveals, more starkly than anything else, why the question of what time is made of sits at the absolute frontier of physics. Here is the problem. If you want to write a quantum theory of gravity, you need to describe the geometry of space-time as a quantum state. Space-time is the thing being quantized. The curvature, the shape, the structure of space-time itself must be described by a wave function, just as the position of an electron is described by a wave function in ordinary quantum mechanics. The wave function of the universe would describe all possible geometries of space-time simultaneously, in a quantum superposition, with each geometry having a certain probability amplitude. This is the logical extension of quantum mechanics to gravity. In the late 1960s, two physicists, John Archibald Wheeler and Bryce-DeWitt, derived the equation that should govern this wave function of the universe. It is called the Wheeler-DeWitt equation. It is the gravitational analogue of the Schrödinger equation. Just as the Schrödinger equation describes how the wave function of a particle evolves with time, the Wheeler-DeWitt equation should describe how the wave function of the entire universe evolves. But here is the extraordinary thing. The Wheeler-DeWitt equation contains no time variable. Time does not appear in it, at all. Let that sink in for a moment. The equation that is supposed to describe the quantum behavior of the universe itself, the equation that should contain all of physics, appears to be timeless. There is no parameter in the equation that tells you what happens next, or what happened before, or how anything changes from one moment to another. The wave function described by this equation does not evolve. It simply is. It is a static, unchanging mathematical object, a fixed quantum state of the entire universe, frozen, without change, without flow, without anything that could be called the passage of time. This seems deeply paradoxical. We experience time. We see things change. Stars are born and die. Particles decay. People are born, grow old, and pass away. Change is the most obvious feature of reality. How can the fundamental equation describing the universe contain no time, no change, no evolution? How can a timeless equation describe a universe that is so obviously filled with time? This is the problem of time in quantum gravity. It is not a problem of writing the equations incorrectly. The Wheeler-DeWitt equation is derived carefully, following the standard rules for constructing a quantum theory from a classical one. The absence of time is not a mistake. It is a consequence of something deep about the structure of general relativity itself. Here is why time disappears. In ordinary quantum mechanics, the Schrödinger equation has the form where the change of the wave function with respect to time equals the Hamiltonian acting on the wave function. The Hamiltonian is the mathematical object representing the total energy of the system. It drives the evolution. It tells the wave function how to change over time. Time is the external parameter, and the Hamiltonian generates the changes. But in general relativity, the total energy of the universe, the Hamiltonian, is zero. Not approximately zero, exactly zero. This is a mathematical consequence of the way general relativity describes gravity. The gravitational energy and the matter energy cancel each other precisely. The total comes to zero. When you quantize this constraint, when you apply the standard quantum mechanical rules to construct the Wheeler-DeWitt equation, you get a wave function whose Hamiltonian is zero. And if the Hamiltonian is zero, there is no evolution. Nothing changes. The equation reduces to a constraint that the wave function must satisfy, not a description of how it evolves in time. This result troubled physicists deeply. In the 1970s and 1980s, researchers including Carol Kuchar and many others explored the problem from numerous angles, proposing different interpretations and possible solutions. The debate continues to this day. It remains one of the most actively discussed issues in theoretical physics. One interpretation is that time, as we experience it, is not a fundamental feature of the universe at all. Instead, time might be something that emerges from the relationships between physical quantities within the universe itself. Perhaps what we call time is really just the changing relationship between different parts of the universe. The hand of a clock moves relative to the background. Atoms oscillate relative to each other. The universe expands relative to the density of matter. These relationships change, and we call that change time. But there might not be any external clock ticking in the background. There might be only the internal relationships between things, evolving relative to each other. In this view, time is not a fundamental ingredient of reality. It is a derived quantity, a way of describing the correlations between quantum subsystems of the universe. Another interpretation is that the Wheeler-DeWitt equation, while mathematically correct, needs to be supplemented with an additional structure that reintroduces time. Perhaps the way we extract time from the equation requires choosing one physical variable to serve as a clock and describing the evolution of everything else relative to that chosen variable. Different choices of clock variable lead to different descriptions of time, but all of them are physically equivalent. This approach preserves some notion of time, but makes it observer-dependent and relational rather than absolute and external. These ideas are deep and technically complex. They are not idle philosophical speculation. They are active areas of mathematical physics research with precise equations, theorems, and careful logical arguments supporting and challenging various positions. But what matters for our purposes is the central message. When you try to combine quantum mechanics with general relativity, time as we normally understand it disappears from the fundamental equations. This strongly suggests that time, at the deepest level, is not the simple, absolute external background that standard quantum mechanics assumes. Something more subtle is going on. This brings us to a question that many people ask when they first encounter these ideas. Is there a particle of time? Is there a fundamental unit, a building block, some smallest piece of time, analogous to how photons are the smallest pieces of light and quarks are the smallest pieces of nuclear matter? The short answer is no. There is no confirmed time particle. No experiment has ever detected one. No standard theory predicts one with confidence. There have been occasional proposals throughout the history of physics for a smallest unit of time, sometimes called a chronon. The idea dates back at least to the mid-20th century, when some physicists speculated that time might be discrete rather than continuous, jumping from one moment to the next in tiny steps rather than flowing smoothly. But these proposals have never gained wide acceptance, and no experimental evidence supports them. The concept of a chronon is easy to misunderstand. It is sometimes presented as though physicists have discovered or are on the verge of discovering the atom of time. But this is not the case. A chronon is a hypothetical idea, a possibility that some theoretical frameworks have explored. It is not a confirmed entity. It is not part of the standard model of physics. It does not appear in quantum mechanics or general relativity. It is a speculation, one among many, about what might happen at scales far below what any experiment can currently reach. And this connects to an even more common source of confusion: the Planck time. You may have heard of the Planck time described as the smallest possible unit of time, the briefest interval that could ever exist, the pixel of time's timeline. But this description, while evocative, is misleading in important ways. Understanding what the Planck time actually is and what it is not is essential for answering our central question honestly. The Planck time is derived from three fundamental constants of nature: the speed of light, Planck's constant from quantum mechanics, and the gravitational constant from general relativity. When you combine these three constants in a specific way, the mathematics gives you a time value of approximately 5.4 times 10 to the negative 44 seconds. That is unimaginably small. It is smaller than any time interval ever measured by any instrument, by a margin of many orders of magnitude. The best atomic clocks can resolve time intervals down to about 10 to the negative 19 seconds. The Planck time is about 25 orders of magnitude smaller than that. We are nowhere close to measuring it directly. The significance of the Planck time is not that it is the smallest possible unit of time. The significance is that it marks the scale at which our current theories stop being reliable. General relativity works beautifully at large scales. Quantum mechanics works beautifully at small scales. For most of physical reality, these domains do not overlap, and the two theories coexist peacefully. The Planck scale is where this peaceful coexistence breaks down. At the Planck time and the Planck length, both quantum effects and gravitational effects are equally strong. You cannot ignore either one. You need a theory that incorporates both simultaneously. But we do not have such a theory. General relativity is not a quantum theory. Quantum mechanics does not include gravity in any fundamental way. At the Planck scale, we need quantum gravity, a unified framework that handles both. And as we have seen, constructing quantum gravity is extraordinarily difficult, in part because of the problem of time. So when someone says the Planck time is the smallest possible unit of time, what they should say is that the Planck time is the scale below which our current understanding of physics cannot make reliable predictions. It is not a confirmed fact about the structure of time. It is a statement about the limits of our theories. Time might be discrete at the Planck scale. It is possible. Some speculative approaches to quantum gravity suggest this. But it is equally possible that time remains continuous even below the Planck scale, and that the Planck time simply marks where we need new theoretical tools, rather than where time itself runs out. We genuinely do not know which possibility is correct. No experiment has reached this scale. No confirmed theory resolves the question. The Planck time is a signpost marking the frontier of knowledge, not a proven feature of time's fundamental structure. This is an important point to get right, because the popular imagination tends to latch onto the Planck time as though it has been confirmed, as though physicists have definitively shown that time is made of tiny discrete frames, each one Planck time long, ticking along like the frames of a movie. This image is vivid and appealing, but it goes far beyond what the evidence supports. It is a hypothesis, not a fact. Let me be very clear about what we do know and what we do not know at this stage. We know that general relativity treats time as part of a dynamic physical spacetime that curves and stretches in response to matter and energy. This is confirmed by experiment to extraordinary precision. We know that standard quantum mechanics treats time as an external parameter, not a quantum observable, outside the system being described. This is the mathematical structure of the theory, confirmed by its spectacular predictive success. We know that when you try to combine these two theories, the Wheeler-DeWitt equation emerges, and time disappears from the fundamental description of the quantum universe. This is a mathematical result derived from well-established principles. We know that the Planck time marks the scale where both quantum and gravitational effects become simultaneously important, and our current theories lose reliability. This is derived from the fundamental constants of nature. What we do not know is what actually happens at the Planck scale. We do not know whether time is discrete or continuous at that level. We do not know whether the disappearance of time from the Wheeler-DeWitt equation means time is truly not fundamental, or whether there is some subtle way to recover time from the equation that we have not yet understood. We do not know whether time is made of some deeper quantum substance we have not yet discovered. We do not know whether the concept of time even applies at the Planck scale, or whether it gives way to something entirely different, some structure we do not yet have the language or mathematics to describe. And this honest acknowledgement of what we do not know is itself scientifically important, because it tells us where the frontier is. It tells us exactly which questions need answering. It tells us what a successful theory of quantum gravity would need to explain. Any candidate for a theory of quantum gravity must address the problem of time. It must explain how the time of our everyday experience, the time measured by quantum clocks, the time that bends near massive objects, emerges from a framework that might not contain time as a fundamental ingredient. The mismatch between quantum mechanics and general relativity regarding time is not a curiosity or a footnote. It is one of the primary reasons quantum gravity remains unsolved. Every attempt to quantize gravity must confront this issue directly. If you try to quantize general relativity using the standard techniques that work for the other forces, you immediately encounter the problem of time. The Hamiltonian constraint eliminates time from the equations. The physical interpretation of the resulting timeless wave function becomes deeply unclear, and the mathematical difficulties compound rapidly, producing infinities and inconsistencies that resist all the standard tools developed for quantum field theory. This is why many physicists believe that solving quantum gravity will require a genuinely new understanding of time. Not just a technical adjustment to the equations, not just a clever mathematical trick, but a fundamental reconceptualization of what time is. Perhaps time is emergent, arising from deeper quantum processes in the way that temperature arises from the motion of molecules. Perhaps time is relational, existing only as a measure of how different parts of the universe change relative to each other, with no absolute external flow. Perhaps time is discrete, built from fundamental units at the Planck scale. Perhaps it is something else entirely, something we have not yet imagined. Each of these possibilities would transform physics. Each would change what it means to ask what time is made of, and each has its advocates among theoretical physicists, supported by careful mathematical arguments and creative theoretical frameworks. But none has been confirmed. None has the decisive support of experimental evidence. The question remains open. What is clear is this: the tension between quantum mechanics and general relativity regarding time is not a failure of either theory within its own domain. Both theories work brilliantly where they are designed to work. The tension arises specifically at the boundary between them, at the Planck scale, in extreme environments like the centers of black holes and the earliest moments of the universe, where both quantum effects and gravitational effects are simultaneously crucial. These are the environments where the nature of time should reveal itself most clearly. and these are precisely the environments we cannot yet probe experimentally or describe theoretically with confidence. The universe is telling us something. It is telling us that our two best theories of physics describe time in incompatible ways. It is telling us that this incompatibility is not a surface-level disagreement, but a deep structural clash about the fundamental nature of reality. It is telling us that resolving this clash will require new ideas, new mathematics, and perhaps new experiments that push the boundaries of what we can observe and measure. And it is telling us that the answer, when we finally find it, will reveal something profound about what time actually is at the most fundamental level. Whether it is a basic ingredient of reality or an emergent phenomenon, whether it is continuous or discrete, whether it is made of something we have not yet discovered, or whether asking what it is made of is simply the wrong question. We do not have that answer yet, but we are closer than ever to knowing where to look. And the place we need to look is the unresolved frontier where quantum mechanics and gravity meet, where our most fundamental theories collide, and where the nature of time itself hangs in the balance. We have arrived at the frontier, the place where confirmed physics ends and the most daring ideas in theoretical physics begin. We have seen that quantum mechanics treats time as an external parameter. We have seen that general relativity treats time as part of the dynamic fabric of spacetime. We have seen that combining these two theories leads to the Wheeler-DeWitt equation, where time disappears entirely from the fundamental description of the universe. And we have seen that the Planck time marks the boundary where our known theories stop being reliable, without telling us definitively what lies beyond. Now we need to explore what physicists think might be happening at that boundary, because even without a confirmed theory of quantum gravity, some of the sharpest minds in physics have developed frameworks that offer glimpses, tentative and speculative, of what time might be at the deepest level. These ideas are not confirmed. None of them have the decisive experimental backing that would elevate them from hypothesis to established theory. But they are not wild speculation either. They are careful mathematical frameworks built from the foundations of known physics, pushed into regimes where new structures might emerge. And taken together, they paint a picture that is strange, surprising, and profoundly different from how most people think about time. One of the most striking ideas is that time might not be fundamental at all, that it might be emergent. This word has a specific meaning in physics. Something is emergent when it arises from the collective behavior of more fundamental components, even though those components do not individually possess the property in question. Temperature is the classic example. A single molecule does not have a temperature. But when you have trillions upon trillions of molecules moving and colliding, their collective average kinetic energy produces something we experience as temperature. Temperature is real. You can measure it. It governs whether water freezes or boils, but it is not a fundamental property of the universe. It is a derived quantity, emerging from the statistics of enormous numbers of microscopic events. Some physicists believe time might work the same way. At the most fundamental level, at the Planck scale, there might be no time at all. Instead, there might be some collection of more basic quantum entities, quantum states of geometry, quantum bits of information, quantum relationships between fundamental degrees of freedom that do not individually involve time in any way. But when enormous numbers of these fundamental entities interact, when they are coarse-grained and averaged over, something that looks like the smooth flow of time emerges from their collective behavior. Time, in this view, would be like temperature. Real, measurable, physically consequential, but not a basic ingredient of reality, an appearance arising from the statistics of something deeper. This idea is not new. It has roots stretching back decades, but it has been developed most carefully within specific theoretical frameworks. One of the most interesting is the thermal time hypothesis, proposed by the physicists Alain Connes and Carlo Rovelli in the 1990s. Their starting point was a deep and surprising connection between time and thermodynamics, the branch of physics dealing with heat, energy, and entropy. In classical thermodynamics, there is a quantity called entropy that measures the disorder or randomness of a system. The second law of thermodynamics says that entropy tends to increase over time. Things naturally evolve toward greater disorder. Hot objects cool. Organized structures decay. Energy spreads out from concentrated to diffuse. This tendency is so universal and so robust that many physicists consider it more fundamental than most other laws of physics, and it is intimately connected to our experience of time. We remember the past, but not the future. Causes precede effects. Eggs break but do not spontaneously reassemble. The directionality of time, what physicists call the arrow of time, seems deeply connected to the increase of entropy. The thermal time hypothesis takes this connection and turns it inside out. Instead of saying that entropy increases as time passes, the hypothesis proposes that the flow of time is itself a consequence of the statistical properties of the quantum state of the universe. Given a quantum state that describes the universe without any reference to time, without any explicit time parameter, you can still define a notion of flow by looking at how the state relates to certain statistical quantities associated with thermodynamics. The mathematics of statistical mechanics, the framework developed by Ludwig Boltzmann and Josiah Willard Gibbs in the late 1800s, provides a natural notion of flow even in a timeless system. The thermal time hypothesis identifies this statistical flow with what we experience as the passage of time. In simpler terms, the idea is this. The universe might be in a timeless quantum state, as the Wheeler-DeWitt equation suggests. But when we observe the universe from our limited perspective, unable to see all the microscopic details, unable to track every quantum degree of freedom, we experience a statistical flow that we interpret as time. Time is not built into the foundations. It emerges from our incomplete knowledge of the full quantum state. It is a thermodynamic quantity, arising from the same statistical averaging that gives rise to temperature and entropy. This is a beautiful idea. It offers a potential resolution of the problem of time in quantum gravity. If time is emergent, then the fact that it disappears from the Wheeler-DeWitt equation is not a problem. It is expected. Time is not supposed to be in the fundamental equation. It is supposed to emerge at a higher level of description, the way temperature emerges from molecular motion. The fundamental level is timeless. Time appears only when you look at the universe in a coarse-grained way, averaging over details you cannot access. There is another approach to emergent time that is more concrete and more directly connected to the Wheeler-DeWitt equation. It was proposed in 1983 by the physicists Don Page and William Wouters, and it has become one of the most discussed ideas in quantum foundations and quantum gravity over the past decade. The Page-Wouters mechanism, as it is now called, offers a remarkably specific answer to a question that seemed almost unanswerable. If the quantum state of the universe is truly timeless, as the Wheeler-DeWitt equation suggests, how can anything within that universe experience the passage of time? The idea works like this. Imagine the universe is in a single, static, unchanging quantum state, exactly as the Wheeler-DeWitt equation describes. No time parameter, no evolution, just one fixed quantum state that satisfies a constraint equation. Now, divide the universe into two parts. One part is a physical clock, some quantum system whose internal states change in a regular way. The other part is everything else, the rest of the universe that you want to describe. Even though the total quantum state of the universe is static and timeless, the two subsystems can be entangled with each other. Quantum entanglement means the states of the two parts are correlated. When the clock subsystem is in one particular state, the rest of the universe is in a corresponding state. When the clock subsystem is in a different state, the rest of the universe is in a different corresponding state. These correlations exist within the single, static wave function. Nothing is changing, nothing is evolving. But the correlations are there, built into the structure of the timeless quantum state. Here is the key insight. If you are inside the universe, if you are part of the non-clock subsystem, and you look at the clock, you see a specific clock reading. And conditioned on that reading, the rest of the universe appears to be in a specific state. If you look at the clock again and see a different reading, the rest of the universe appears to be in a different state. From your perspective inside the universe, it looks exactly as though time has passed and the universe has evolved from one state to another. But from the outside perspective, from the perspective of the total quantum state, nothing has changed. The state is the same as it always was. The appearance of change, the appearance of time, arises entirely from the quantum entanglement between the clock and everything else. This is extraordinary. It means time might be nothing more than quantum entanglement between subsystems of a globally timeless universe. The flow of time, the sense that one moment follows another, the fact that the universe appears different at different clock readings, all of this can be recovered from a completely static quantum state through the mechanism of entanglement alone. Time is not imposed from outside. It is not a fundamental parameter. It emerges from within, from the quantum correlations between parts of the universe. The Page-Wouters mechanism was initially regarded as an elegant curiosity, a thought experiment demonstrating a conceptual possibility. But in recent years, it has attracted renewed and serious attention. In 2013, a team of researchers performed a laboratory experiment using entangled photons that directly demonstrated the mechanism. They created a quantum system in which an external observer saw a static, unchanging state, while an internal observer, defined by one subsystem of the entangled pair, experienced what looked like ordinary quantum evolution in time. The two descriptions were mathematically equivalent, exactly as Page and Wouters had predicted. The experiment did not prove that our universe works this way. It was a tabletop analog, a proof of concept using photons in a laboratory. But it showed that the mechanism is physically real. It is not just mathematics on paper. Quantum entanglement genuinely can produce the appearance of time from a timeless state. This connects beautifully to the thermal time hypothesis, but approaches the problem from a different angle. The thermal time hypothesis explains the flow of time through statistical mechanics and thermodynamics. The Page-Wouters mechanism explains it through quantum entanglement and the internal structure of a timeless wave function. Both suggest time is emergent. Both offer specific mathematical frameworks. Both remain unconfirmed as descriptions of the actual universe. But together, they demonstrate that the idea of emergent time is not vague philosophical speculation. It is precise physics with concrete mechanisms and testable analogues. But the thermal time hypothesis is not confirmed. It is a proposal, a framework, a mathematical possibility that has been explored in specific models but not tested against experiment. It makes conceptual sense. The mathematics is consistent, but whether it correctly describes the actual universe is an open question. There are technical challenges that remain unresolved, and there are competing proposals that offer very different pictures of what might be happening. One such competing picture comes from causal set theory, a framework developed by Raphael Sorkin and others beginning in the 1980s. Causal set theory takes a radically different approach to the structure of spacetime. Instead of assuming spacetime is a smooth, continuous fabric that might or might not be quantized, causal set theory proposes that spacetime is fundamentally discrete. It is made of individual events, points in spacetime, connected by causal relationships. Some events can influence others, some cannot. The pattern of these causal connections defines the structure of spacetime. In causal set theory, the fundamental objects are not points in a smooth manifold, but elements of a discrete set. These elements are the atoms of spacetime, in a loose sense. They are connected by a partial ordering, a mathematical structure that says which elements come before which. This ordering is the causal structure. Event A can influence event B if A is in B's causal past. Otherwise it cannot. The entire geometry of spacetime, its distances, its curvature, its dimensionality, emerges from the pattern of these causal relationships among discrete elements. And time, in this framework, has a very specific role. Time is the ordering. Time is the structure that tells you which events come before which. It is not something separate from the causal set. It is part of the causal set's fundamental structure. But it is also discrete. There is no continuous flow of time in causal set theory. There are individual events, and there is the ordering between them. Between any two causally connected events, There is a finite number of intervening events, not a continuous interval. Time, in this view, is granular. It comes in discrete steps, each step corresponding to one element of the causal set. The typical scale of these discrete elements is expected to be around the Planck scale. Each element of the causal set corresponds to roughly 1 Planck volume of spacetime, a region about 1 Planck length across and 1 Planck time in duration. Below this scale, there is no spacetime at all. There are only the elements and their connections. Smooth, continuous spacetime emerges when you zoom out, when you look at enormous numbers of elements together, the way a smooth photograph emerges from enormous numbers of individual pixels. This picture is very different from the thermal time hypothesis. In the thermal time view, time is not fundamental at all. It is a statistical illusion arising from our incomplete knowledge of a timeless quantum state. In the causal set view, time is fundamental. It is built into the deepest structure of reality as the ordering of discrete spacetime elements. Both views are speculative. Both are internally consistent mathematical frameworks. Both address the problem of time in quantum gravity, but they give very different answers to our central question. Loop quantum gravity, one of the leading approaches to quantum gravity, offers yet another perspective. In loop quantum gravity, space is quantized. Area and volume come in discrete units, quantized in multiples of Planck scale quantities. Space is not smooth and continuous at the smallest scales. It is made of discrete quantum units called spin networks, graphs with labeled edges and vertices representing quantum states of geometry. The geometry of space, the distances and angles and curvatures we measure at large scales, emerges from the collective properties of these spin networks when you zoom out from the Planck scale. But time in loop quantum gravity is more complicated. The theory describes how spin networks evolve, how the quantum geometry of space changes. This evolution produces structures called spin foams, which represent the quantum history of spacetime. But the relationship between this quantum evolution and the time of our everyday experience is not straightforward. In some formulations, time emerges from the dynamics of the spin foam rather than being imposed from outside. In others, a notion of time is built in from the start as a parameter governing the evolution. The status of time in loop quantum gravity remains an active area of research and debate. Carlo Rovelli, one of the founders of the theory, has argued extensively that time is not fundamental, that at the deepest level, the universe is described by relationships between quantum events, and time is our way of organizing those relationships into a sequence. He has written that time is simply what we call the way things change relative to each other, not a separate entity flowing in the background. Other researchers within the loop quantum gravity community hold different views, arguing that some notion of time must survive at the fundamental level to make the theory physically meaningful. There are also perspectives coming from a very different direction. The holographic principle, inspired by the physics of black holes and developed in part through the ADS-CFT correspondence proposed by Juan Maldacena in 1997, suggests that the information content of a region of spacetime can be encoded on its boundary. The physics of a three-dimensional volume can be completely described by a two-dimensional surface surrounding it. This remarkable idea, which sounds impossible but is supported by strong mathematical evidence, has deep implications for the nature of spacetime and potentially for the nature of time. In the holographic framework, spacetime itself might be an emergent phenomenon. The fundamental description might live on a lower dimensional boundary where the physics does not include gravity and where time plays a more conventional role. The spacetime we experience, with its 3 dimensions of space and 1 of time, might emerge from this boundary description through a complex mathematical mapping. In this picture, the time inside the spacetime is not the same as the time on the boundary. The relationship between them is subtle and depends on the specific geometry involved. This suggests that time as we experience it might be a derived quantity, a shadow of something more fundamental happening in a different mathematical framework. These ideas are technically sophisticated and far from settled. The ADS-CFT correspondence works precisely only in a specific mathematical setting that does not exactly match our actual universe. Extending these results to cosmology, to the real expanding universe we live in, remains an open and very difficult problem. But the holographic principle has taught physicists to take seriously the possibility that spacetime, including time, might not be fundamental. That the deepest description of reality might involve structures and concepts very different from the space and time of our everyday experience. So where does all of this leave us? Let me be very honest about what we know and what we do not know, because honesty about the limits of our knowledge is just as important as explaining what we have discovered. The honest answer to the question of what time is made of, according to quantum physics, is that we do not know, and we should not pretend otherwise. But saying we do not know is not the same as saying we know nothing. We know an enormous amount about how time works. We know that quantum mechanics uses time as the parameter governing the evolution of quantum states. We know that this treatment has been confirmed by a century of experiments with extraordinary precision. We know that physical clocks built from quantum systems can measure time with an accuracy that exceeds 1 part in 10 to the 18th power. We know that general relativity describes time as part of a dynamic physical spacetime that curves and stretches in response to matter and energy. We know that this too has been confirmed by experiment to remarkable precision, from the bending of starlight to the detection of gravitational waves to the direct measurement of gravitational time dilation with atomic clocks. We know that combining these two theories leads to deep and unresolved tensions. We know that the Wheeler-DeWitt equation, the fundamental equation of quantum gravity as currently formulated, contains no time. We know that the Planck time marks the scale where our current theories lose reliability. We know that several carefully constructed theoretical frameworks suggest time might be emergent, arising from more fundamental quantum structures that do not themselves involve time. And we know that other frameworks suggest time might be fundamental but discrete, built from atomic elements at the Planck scale. What we do not know is which, if any, of these frameworks correctly describes reality. We do not know whether time is continuous or discrete at the smallest scales. We do not know whether it is fundamental or emergent. We do not have a confirmed theory of quantum gravity. And without one, the deepest questions about the nature of time remain genuinely open. This is not a failure of physics. This is physics working exactly as it should. Science progresses by identifying what it does not know and then systematically working to close those gaps. Physicists know exactly where the problem is. They know exactly which questions need answering. The problem is unsolved, but it is not undefined. It is sharp, precise, and well characterized. And there is reason for cautious optimism. New tools are emerging. Gravitational wave detectors like LIGO and the planned space-based LISA mission are opening new windows on the universe, probing environments where space-time curvature is extreme and quantum gravity effects might leave subtle imprints. Precision measurements of the cosmic microwave background radiation continue to improve, potentially revealing signatures of physics from the earliest moments of the universe when quantum gravity was important. Quantum computers are advancing rapidly, offering the potential to simulate quantum gravitational systems that are too complex for conventional computation. And theoretical progress continues, with new mathematical structures and conceptual breakthroughs appearing regularly. One thing that these theoretical explorations have already taught us, even without experimental confirmation, is that time is not what common sense suggests. Common sense tells us that time flows uniformly, carrying us from past to future at a steady rate, that it is the same everywhere, that it exists independently of everything else, that it is simple, absolute, and self-evident. Quantum physics and general relativity have already shown that every one of these common sense assumptions is wrong. Time is not uniform. It runs at different rates depending on gravity and motion. Time is not the same everywhere. It depends on where you are in a gravitational field. Time is not independent of everything else. It is woven into the physical fabric of space-time, responding to the presence of matter and energy. And time is emphatically not simple. Its nature involves the deepest unresolved questions in all of physics. But there is something we should be careful not to do. We should not conclude that because time is mysterious, it is therefore nothing, that because we cannot explain its ultimate nature, it must be an illusion, that because the Wheeler-DeWitt equation contains no time, the experience of time passing must be somehow fake. This is a mistake that appears frequently in popular discussions of physics, and it goes far beyond what the science actually says. Even if time is emergent, it is still real. Temperature is emergent. It arises from molecular motion and is not a fundamental property of individual particles. But temperature is not an illusion. You can measure it. It determines whether water is ice, liquid, or steam. Temperature being emergent does not make it unreal. It makes it real at a different level of description than the fundamental microscopic level. If time is emergent in a similar way, it would still be real. It would still govern the evolution of physical systems. It would still be the thing that clocks measure. It would still be the framework within which change occurs. Its ontological status might shift from fundamental to derived, but its physical reality would remain intact. Similarly, we should avoid the opposite extreme. We should not claim that quantum physics has already solved what time is. It has not. No current theory provides a complete, confirmed, experimentally validated answer to the question of what time is made of. Anyone who tells you that physics has definitively shown time is made of discrete Planck-scale units, or that time is purely an illusion created by consciousness, or that time is made of information, or that time is made of energy, is going beyond what the evidence supports. These are not established results. They are speculations, hypotheses, or misunderstandings. Some of them are inspired by genuine physics, others are not, but none of them are confirmed. The honest scientific position is this: current physics uses time in two different and incompatible ways. It describes how things change with time with extraordinary precision. It measures time with accuracy that exceeds anything else in experimental science. But it does not explain what time fundamentally is. It does not show that time is made of any confirmed substance, particle, or building block. It does not resolve whether time is fundamental or emergent, continuous or discrete, absolute or relational. These remain open questions, sitting at the absolute frontier of theoretical physics, waiting for the theory of quantum gravity that will finally answer them. And there is something deeply beautiful about this situation if you look at it the right way. Because it means we are living at a moment in the history of science where one of the most fundamental questions about the nature of reality remains genuinely unanswered. We know enough to ask the question precisely. We know enough to rule out many wrong answers. We know enough to sketch the outline of what a correct answer might look like. But we do not yet know the answer itself. This is rare in modern physics. Most of the easy questions have been answered. Most of the straightforward problems have been solved. What remains are the genuinely hard problems, the questions that resist centuries of effort, the puzzles that require entirely new ways of thinking. The nature of time is one of those problems, perhaps the deepest of all. Every second that passes, you are experiencing something that physics cannot fully explain. Every moment of your life unfolds within a framework whose ultimate nature remains unknown. The clock on your wall, the watch on your wrist, the phone in your pocket, all of them measure something real, something physical, something that governs every process in the universe, from the decay of subatomic particles to the expansion of the cosmos. But what that something actually is at the deepest level is a question that remains open. Quantum physics tells us that everything in the universe evolves in time. Particles move, fields fluctuate, states change, energy transfers from one form to another. All of this happens in time. All of it is described by equations that include time as an essential ingredient. But those same equations never tell us what time itself is made of. They use time constantly, but explain it never. This tension, this gap between using time and understanding time, between measuring it with breathtaking precision and explaining its fundamental nature, is one of the most profound and consequential tensions in all of human knowledge. It tells us that our understanding of the universe, as successful and precise as it is, remains fundamentally incomplete. There is something about the deepest structure of reality that we have not yet grasped. Something that involves time in a way we do not yet understand. And the resolution, when it finally comes, will be one of the greatest achievements in the history of human thought. Because it will not just answer a question about physics, it will answer a question about the very framework within which all questions are asked and all answers unfold. It will tell us what the thing is that separates the past from the future, what the thing is that allows change to occur, what the thing is that makes the universe a story rather than a frozen snapshot. Every experiment you have ever performed, every thought you have ever had, every breath you have ever taken, has happened within time. And what that time is made of, whether it is made of anything at all, whether asking what it is made of is even the right question, remains one of the last great mysteries at the heart of physics. We are not ignorant about time. We are more knowledgeable about how time works than any generation in human history. We measure it more precisely than any other physical quantity. We understand its behavior under conditions ranging from the everyday to the extreme, from the ticking of a wristwatch to the warping of spacetime near a black hole. But we do not yet know what it fundamentally is. And that gap, that one remaining gap between measurement and understanding, between using time and explaining time, is where the next revolution in physics will begin. Thank you for joining me on this journey into one of the deepest questions in science. If you found this exploration valuable, a like or subscribe helps keep these deep investigations going. It's a small thing, but it genuinely makes a difference. And the next time you glance at a clock, remember what you've learned tonight. That clock is counting quantum oscillations with extraordinary precision. It is measuring something real and physical. But what it is measuring, what time actually is at the most fundamental level, remains one of the greatest open questions in the history of human understanding. And that question, honest and unresolved, is itself something worth appreciating. Good night.